Okay guys, so we're going to start over here with this lovely piece of 40 by 40 cast iron bar. And what sucks about this little exercise that I'm doing here is I have one of those awesome DeWalt Portabands that my lovely wife purchased for me. But I had a really hard time getting replacement blades for this thing. So I had to get back into the old elbow grease scenario, and yeah, I did a little blade change there, found a slightly coarser blade, and now I'm just giving it the beans. I've got the vacuum cleaner on at the bottom there. It just helps to get that fine particulates and cast iron dust out of the air. I don't like breathing that stuff in. I already struggle with my sinuses a lot here in the middle of the desert. And I don't want to breathe any additional even organic, but definitely not non-organic material. Not good for the lungs. Okay, so yeah, just doing a quick little cleanup here. I'm not the most organized, most clean individual you'll ever see in a workshop. My cleaning and my mindset is kind of on the same level. It's a bit of chaos. So I just used that long end mill there to clean up the sides of this. So the whole idea about this cast iron bar is this bolts up onto the back of the gantry, straight through the linear rail, to give it some torsional and just rigidity. Weight and cast iron is really good at absorbing vibration. So my hope for this exercise is that this is really going to improve the rigidity of the machine, the vibration damping of the machine, and just overall increase my ability to take a faster, deeper, more aggressive cut, and also give a better finish. So I'm just cleaning the top off here. I'm only dusting off the one side of this, just the side that's going to sit flat up against the back of the gantry. This is a little dovetail cutter with two carbide inserts, but this is that polished inserts that are specifically for aluminium. I use this on everything. They don't last as long, but man, do they leave a beautiful finish. Just beautiful. These inserts are razor sharp. I did a little test cut on a piece of 4140 chromoly in its annealed state, and it just leaves a beautiful finish. I love this tool. I use this specific tool a lot. I use this as a fly cutter. I use this to remove a considerable amount of material if I need to. I just really like it. So I'm just cleaning off the top of this. This is probably not the best way to do it, because I reposition this bar over it so that I can catch the other end of it as well. Just tap it down to make sure that it's flush on the two vices there. This needn't be absolutely perfect, but obviously you want to get it as true and as perfect as possible. So I'm literally just dusting off the top, just making sure that it's clean. I had a really long time to think about, I'm doing this voiceover here about a month after I actually shot this, and I did the work. I've been really busy for the last month. With my wife is 7 months pregnant now, and just so much planning and busy at work, and just, life in general. I mean, everyone knows how hectic life gets. So yeah, I'm finished the dust off there. I actually had to come back after this and do a substantial amount of machining more on those cast iron bars, because I kind of changed my mind on the fly on when exactly I wanted to fit those bars on the back. But anyway, so I'm breaking up that setup. I'm putting my Chinesium CNC vise back on here. So what I'm doing here is I'm basically, instead of using just one spindle clamp, I'm going over to a 2 spindle clamp setup. I want the two clamps to be significantly further away from each other to give more support to the spindle. I do move the spindle around quite a bit, depending on what I'm cutting. When I'm cutting carbon fiber on this, I actually move the spindle all the way down so that it can reach down low on the bed. And then there's a significant portion of that spindle sticking out. So I lose a bit of rigidity. But it's fine because when you mill the carbon fiber, you really don't have a lot of cutting forces on there. So this is mainly for when I do more heavier milling. So what I'm basically doing is I'm putting a little hole through the center on each of the clamping sides of this, because I want to put a bolt in there so that I can clamp the spindle down without putting the two main bolts through there. So I'm just going to drill there, go through of that. I love these carbide drill bits. They're just awesome. They just go through everything like butter. So I'm just drilling the holes through there, and then we're going to tap that and put some bolts in there. And that will allow me to clamp both of these clamps down onto the spindle, basically using the spindle as an alignment tool to get these two clamps perfectly aligned. And then I'm going to mold these two clamps perfectly flat relative to each other, and put some chamfers on there and just clean the whole thing up. You'll see I'm doing a lot of bolt hole modifications on this, because the specific Allen cap bolts that I want to use, they're not long enough to go all the way through them the way I want to use it. Plus they sit proud of the surface where they bolt through, and I want to countersink them and just get them down to sit flush or below the surface. So now I'm just chasing a tap through there so that I can come in with a M6 bolt to basically clamp this spindle. I'm using a very long, deep reach tap there. They've been working really well for me. I get them off of AliExpress. They're dirt cheap, and they're actually reasonable quality. I've not had any issues with them. Just coming in and put a nice little countersink on those holes. I'm just cleaning them up, and then once we finish with this op, I can actually slide the spindle through there, clamp it down, and then start lining those two clamps up properly to mold them to be perfectly flat and true relative to each other. What I do is I basically use the body of the spindle as a reference, and I indicate over the top of the sides of the spindle to get the setup true in the vise. Ultimately, you're never going to get this perfect to the point where you don't have to shim it when it's on the gantry. I just want to get it close so that I need to do minimal shimming afterwards to get the spindle alignment perfect. I'm just chasing those taps through, making sure those threads are nice and clean, and that's basically the end of that first operation. Just cleaning everything out. They were a little bit flimsy because where I drilled and tapped on that open end of those clamps, they were a little bit flexing. I probably could have inserted something into that gap, but this is where we want to get to. I want to clamp both of these, align them, clamp them down solidly on the spindle, and now I can use the spindle basically as an alignment tool, so that when I machine this, I know that all my machining is perfectly true relative to the bore of these clamps, because the spindle basically forces them to align perfectly. And this ended up working out pretty well. Like I said before, I've got very, very limited experience with any of this, with machining, with anything of the sorts. So I'm really, really learning as I go along. Here I'm just checking what the alignment looks like. I just want to get them reasonably aligned before I start machining. I think these are cast spindles with a little bit of machining on them. If you look at some of these surfaces up and close, you can really see that they're not perfectly clean, and they're not perfectly aligned. The surfaces or the texture on all of this is really not perfect. So I'm just indicating off of the one side of the spindle, and then we run over, and then we indicate off of the other side, and I use that left side and right side to align this and get this as true as possible, so that when I cut the surface over these two clamps, that is as true as I can can possibly get them. So you'll see I'm putting a little bit of shim stock in there, just to get this alignment good from the one side to the other side of the spindle, so that when I machine it, that machine surface is really nice and true relative to the side, or parallel to the side of the spindle there. Yeah, so now I'm quite, at this point I was happy with the alignment there. And the first I'm going to go in with this exact same cutter, this dovetail cutter with the aluminium inserts. It's just magic. This thing just leaves a beautiful, beautiful finish. I liked it so much. This is a cheapo Chinese insert tool that I think after this I ended. This is a two. This one is this one has got two teeth on it, or two inserts on it, and I liked this so much that after this I searched for the smallest one I could find that takes 3 inserts, because more is better apparently. And then I can just run it a little bit faster if it's got 3 inserts on it. This mill really doesn't have a lot of RPM behind it. It's 1200 RPM flat out, which is really not sufficient. I do plan on CNCing this mill eventually, and then I want to run it, somewhere between 7 and 9,000 RPM spindle speed if I can get it up there. I do have a 2.6 kilowatt AC servo motor that I'm going to run for the spindle motor, and then I'll just run this on a pulley arrangement to get it up to somewhere between 7 and 9,000 RPM max, to really utilize what you can do with the insert tooling and the end molds, because I really don't think that they're anywhere near as efficient of a material removal rate at low RPM as they can be. So we're just cleaning up both ends here. This insert, this specific tool, I just love this thing. It's such a. I know I'm not supposed to use it for everything, but it just cuts so beautifully that I use this really as a face mill, to face finish things, to remove significant amounts of material, and it just leaves an awesome finish on everything. So there was a bit of learning taking place here for me. Afterwards, I decided to put some chamfers on the edges all around these 2 clamps. And then I saw that when I'm doing conventional milling, it really leaves a horrible finish with the chamfer mill. It recuts the chips, it throws the chips around, it recuts the chips, and it welds them to the surface that I've already cut. And it's not easy to clean it back up again. So I'll show you that in just a moment when we get there. So yeah, all of this footage is basically running at 6 times speed. Otherwise, this video would be 6 hours long, and that just wouldn't work. And no one wants to watch a 6-hour video of an amateur fooling around trying to do stuff. So I'm running all of these. Some of these are at 4x, and some of these are at 6x speed. Here we go, a bit of elbow grease. I can't wait to automate this head. Okay. So the main surface finish here is beautiful. Came out really well. And yeah, at this point I decide I'm going to come in with the chamfer mold, and I just want to put a chamfer on all of it. That really left a beautiful finish. I'm very, very happy with that. I think I'm going to have a quick look at the surface finish here. I was quite happy with that. I must say, the camera does not always do a good job at portraying how good the surface finish is. I mean, you'd really have to play around with the light and everything, and then you'd still not be able to really, portray through the TV screen how good the surface finish on some of these things is. And the same thing goes for sometimes the screen hides how bad some of these surface finishes is. I was really happy with how that came out. Okay, so now we're going to run the chamfer mill through there. That was a climb cut, that was a climb cut. All of this leaves a beautiful finish. And now when I run down the middle, okay, I cut that piece out. When I run down the middle there, I saw a little bit of an issue. And we're going to come back to that now. So you're going to see now I'm doing a conventional cut going up the side of this. And here you can see it leaves a bit of fluff behind the tool that really doesn't look good. It's very jaggedy, very rough. I was really not happy with this. And I'm going to do a little bit of a closer inspection here, and then once I come back down the same side with a climb cut, it just leaves a phenomenal finish on there. And then I basically go back and I climb cut all of these edges that had left this horrible fluffy recut finish, and it basically re-welds that chip onto that surface. You can't just rub it off. You'd have to come in with a really fine file or a piece of sanding paper, fine sanding paper. And yeah, I'm just looking at this and I'm like, ugh, you know, what the heck is going on here? I'm feeling the side that I climb cut. That side is beautiful. Down the middle, one side is beautiful because the one side was a climb cut and one side was a conventional cut. So that looks really bad. And now I'm kind of thinking about this and I'm checking, okay, I'm going to, dial up like 0.1 of a mil and I'm going to come back with this climb cut and I'm going to see what it does. And lo and behold, it leaves a beautiful finish. And I find myself these days doing more and more and more climb cutting. Even with my normal little, brass main nut on the mole with a normal Acme thread. And, there's a lot of backlash on that nut. I find myself, when I'm doing climb cuts, I'm getting a really good finish. And the machine is happier. I get less chatter. Just by, what I've been reading and looking up, a climb cut is not bad for the tool. In terms of tool wear, there's significantly less rubbing on the tool than with a conventional cut. I'm loving the climb cuts more and more. So there we can see... I think I'm going to show it just now, and there we go. Now that's after everything was climb cut, and it just left a beautiful finish on all of these corners, and I was really, really happy with the result that I got here. I think here I'm just pointing out that side looked horrible after that initial conventional mold. And then when I came back with the climb cut, it just cleaned it up fantastically. So, that's how I learn. That's how this is a massive learning curve for me. I don't know much about any of this. Yeah. So, flipped around. Now I'm going to counterbore all the holes where the main Allen caps are going to go through. That's going to pull this down onto the Z-axis saddle, or onto the Z-axis main plate. I'm counterboring these to the point where I get sufficient protrusion of the bolt down the bottom. So what you can see here is I had to space these two M6 Allen caps on the side. I had to space them up with a couple of washers so that I can get a good strong clamp out of them. They were a little bit long to give me a good clamp. And when we come over to this other side to countersink those holes, I actually have to cut through the sides of those washers because they're a little bit in the way. But that carbide counterbore really doesn't care. It doesn't even know those washers are there. It just cuts through them like butter. So here I'm just taking my time. I'm doing an interrupted cut. I don't want the chips to build up and weld onto the counterbore. I've had that happen once before, and then it sucks to try and get that welded chips off of there again. So I'm using a liberal amount of Q20, or sorry, the WD-40. I must say the WD-40 really works magic on aluminium. I love using it. Unfortunately, sometimes depending on what I'm cutting, it's generating a lot of smoke, and I've got a smoke detector in this little workshop of mine. that I've set off once or twice, and then I get the smoke alarm going in the whole building, and that's not cool. It's not good for me, and it's not good for the other residents on my floor. So what I've actually got is I've got a really nice smoke extraction system with carbon filters that I'm going to rig up pretty soon, that I'm going to just use on all of my machines when I cut. And I've got the possibility of making some smoke that could potentially just switch off my smoke alarm. So here you're going to see I'm cutting a little bit of the washers. I've got to just touch the side of the washers here to get my holes to line up really well. But that's no biggie. It cuts through there like butter. Yeah, and then all of these counter bores came out really nicely. Just checking my distance between the holes here. I did not use the DRO for this. I kind of eyeballed them, but they came out really well. This is a spare spindle that I've got because I'm an idiot. At some point I crashed the CNC really hard, and for some reason I thought, based on a bunch of readings that I took and some run out that I saw, I thought that I bent the main shaft of my spindle. So I actually ended up buying a new spindle, and the spindle had arrived and everything, and then one day I just thought, you know what, let me just take a couple of measurements again, and I measured a bunch of stuff, and I was like, oh, the spindle, there's nothing wrong with it. It's all in the collets. The collets that I was using were really bad. They had a tremendous amount of run out in them, and I never measured it before, but because I took measurements after I crashed the spindle, then all of a sudden I was like, ooh, I bent the spindle, and yeah, that was not the case. I did away with that Chinesium collets, and I got some better, higher grade Chinesium collets that were classified as AAs, or I think they classify them 0.003 run out. And they were significantly better, and now I'm stuck with an extra spindle, but all is not lost. When I start building the CNC lathe, the plan that I have for it is that it needs to have fourth axis capability or live tooling capability, and then I will repurpose this spare spindle as the live tooling spindle on the CNC lathe. So all is not lost. It will definitely get good use in the future one day when I get around to building the CNC lathe. But the CNC lathe is really, really high priority for me. It is going to be a phenomenal amount of work, but I am looking forward to the challenge. So yeah, so that's I was happy with that amount of stick out. It was about 1.5 times diameter, and I don't crank the life out of these bolts. And now there's no longer just 4 of them with 1 clamp, but now there's 8 of them with 2 clamps. They are M8s. They sat nice and flush. So I was pretty happy with this. And when I end up fitting this to the main plate on the Z-axis, they do tighten down really, really well without any issues. So here I just came in afterwards with my little deburring tool, and I just deburred all of these holes. And you can see why I had to cut through the washers to get the clearance for the holes there, but that's not an issue. I am going to use different bolts when I eventually put this on, so that I don't have to use that stacked. These carbide counter bores are just magic. They cut through everything, but you do have to mind your chip formation and your chip evacuation. Otherwise, the chips do weld up, and the WD-40 really goes a long way into helping the chip welding not to take place. So yeah, now we're going to go over to the mounting plate where the spindle is going to bolt onto, and we're going to look at how this is going to work. So basically, the spindle is going to mount as such onto that mounting plate. So I need 8 new holes on there, 8 new holes that are aligned well. So what I'm basically doing here is I'm dialing in the rail, which I know is perfectly true because I dialed in this rail on the surface plate, and I'm gonna take a quick measurement here relative to that rail. How straight is that main plate? Because I want to reference off of the side of that main plate in the mill when I machine the 8 new bolt holes for the spindle to bolt onto. So I'm going to measure the run out there, or the error in parallelism there, and then I'm going to take that main plate off, and I'm going to put it back in the mill, and I'm actually going to dial it back in to have that same error that it has right there, right now, and then I'm going to mill it down and true, so that I know that that side is perfectly parallel to the main rail, and then when I put my 8 new bolt holes in there, I know that they are perfectly parallel relative to the rail, or square, or perpendicular, or good. They are good relative to the rail. Okay. So what I'm seeing here is, well, as I'm trying to take this reading, is this little dial test indicator really doesn't like to be side loaded or side swiped because the needle is really, really jumpy. But when I measure it down the length of the needle, the way you see it there now, then the reading is pretty smooth. So I'm just going to lower it down a little bit more here because I actually ran off of the indication, and I end up here with 0.55 millimeters difference from left to right. That's minus 10, minus 15, minus 20, minus 25, minus 30, 40, and we actually end up at minus 55 right there that this drops off. So relative to that top rail, this is off by 0.55 millimeters. From this side over there, 0. It runs down to the far right hand side by 0.55. So I'm going to take this off, put it up in the mill, dial back this error, and then mill it flat so that I know I can use that side as a good reference. Okay, do it. My links here. So the short ones, about 6 months as well. The short ones go onto the old screw. For whatever reason, these screws coming out of this thing smelled like old diff oil. If you know, you know. It was horrible. It has been a wee bit neglected. Right. Last one. There we go. Let's see what's what. Hello. All right. Okay, so we're just going to do a quick cleanup here. I have ordered new ball screws. These are all single ball screws, and I am going to put double nut anti-backlash ball screws on all 3 of these axes. And what a double nut anti-backlash ball screw essentially is it's 2 ball screws that are attached with each other, and it's got an adjustable link between the 2. So you can dial out the backlash between these 2, and that just gives you a better finish, and it's also less prone to chatter because there's no free play for that ball nut to oscillate in. Okay, so there we've dialed back the error. I'm going to come in with that same cutter, and I'm just going to dust this off until it's perfectly true. I think this is going to take a couple of cuts. Again, this thing just left a beautiful finish on here. So at this point, I didn't actually realize how many hours of footage I'd already recorded, and I kind of came to the realization that I'm going to have to split this video up into a two-parter, just to not prolong the agony of the viewers trying to live through all of my amateurness. So yeah, this video, I end up cutting this and making this a two-parter, and then we finish off this portion of the modifications in the second half. That'll hopefully be done next week. And here I am just admiring the reflection coming off of this finish. Yeah, it came out really well. Beautiful reflection coming off there. Good finish. Okay. So now we're going to chamfer the edges on this. As Blondie Hacks would say, it's what separates us from the animals. Good chamfers. And by this time I have now learned my lesson, and I am doing a climb cut on all of these chamfers, and it's just leaving a beautiful finish. Okay, so up next for this is, and this is completely unnecessary, but I'm going to blue this up. I'm going to take it to the surface plate, and I'm just going to scribe a couple of reference lines on this. I don't need the reference lines because I'm going to use the DRO once I've touched off on that brand new reference side that we just mold. We know that that side is now perfectly true to the rail, and when I reference off of that, I know that all my new bolt holes will be perfectly true to the rail. Okay, so this for me is actually just an exercise, practicing these things so that when I really do need it, I've at least done it a little bit and I've got some practice in. So I just printed out this little drawing from Fusion with the new bolt pattern, and that's exactly how far I am going to mount the spindle brackets apart. And I'm not going to transfer the entire bolt pattern on the surface plate with the scribe. I'm just going to transfer a couple of main lines, and it also for me is a little bit of a sanity check, because if I drill any holes and they don't fall on those lines, then I know I'm busy doing something wrong. So it's also just a little self-check for myself. So basically, I'm just explaining here that I chose this bolt pattern because it's going to keep the spindle in the strongest position when I'm doing heavy cuts. But when I'm doing light cuts, like on the carbon fiber, one clamp will be sufficient. Okay, so I'm just on my small little surface plate here with my little height gauge slash scribe. And I'm just going to scribe a couple of the baselines. I'm basically going to split this thing in half. Just drawing a center line and then dialing up and down and putting a couple of more lines on this. Not, like I said, not that I need them. I'm not going to work off of them. For me, it's just a little bit of practice, and I haven't really had the need, but I know the need for this is going to come up big time once I really start getting into modifying this milling machine or the CNC. The long-term plan for this is to do a completely new gantry plate out of 32mm thick aluminium tooling plate, to get rid of that anemic little plate that they use on the gantry from the factory. Honestly, if I knew what I know now, 2.5 years ago, I probably would not have purchased this specific desktop style of CNC mill. I probably would have gone for a different brand. There's a couple of them that are much more competent in this size, much more capable, much more sturdy, with better controllers. I really don't like the Mach 3. To give you an idea, this machine came with no shielding cable on any of the steppers or on the spindle, and it has given me endless grief because the interference on the spindle signals and the stepper motors have tripped out the machine while it's in process multiple times, and I just want to lose my mind when that happens. Really not nice. So I mean, I've had to multiple times start machining apart from scratch again because I've lost it due to that spindle and stepper motor signal interference that just trips out Mach 3 and basically puts it in like emergency stop mode. And it took me such a long time to find this problem, and some of the guys on the interwebs suggested to me that I open up the loom and separate all the spindle and the stepper motor cables away from each other and see if the problem persists, and lo and behold, the problem was gone. So I have already ordered new stepper cables, new spindle cables, all shielded, and I'm going to redo all of the stepper and spindle wiring, and I believe that that will definitely resolve the problem. So yeah, now we just basically I spot drilled all of these holes on this main carrier plate on the Z-axis. I'm going in with my tap drill size, drilling all of them out, and then we will tap all of them to size. And this is going to be where we stop the first half of this specific upgrade session because it's a really long one. I don't want to keep you guys busy for 50 minutes, 60 minutes. It's really not that interesting. Yeah, there's many more upgrades to come to this machine. Like I said, I want to replace that entire base plate that comes from the factory that holds the rails and everything on it. It's a really anemic little hollow extrusion. I'm going to replace that whole section with a 32mm thick tooling plate. I'm going to replace the sides of the gantry with that same 32mm thick tooling plate. And I'm still going to have the cast iron bars, the 40x40 cast iron bars, bolted onto the back of that tooling plate. And once all of that is done, we're going to lay that thing on its side, we're going to box it up, and fill the entire back end of that gantry with epoxy granite. And the reason I'm after all of this rigidity is because I want to upgrade the spindle also eventually with a not necessarily a higher powered spindle, but I'm looking for a ATC spindle. Yeah. So this is it, guys. Thank you very much. If you've stuck around this for the whole video, you are a champion, and I will see you guys again on the next one.